Hello, we're back again here. I'm just trying to get this lined up as always here because I don't have it as much as I would like it. Here we go. So welcome back. In this session, we are going to, I'm going to try to kind of get it I'm going to try to get it so that it is centered here. Oop, I actually have somebody officially watching. So we actually, for the first time, because mostly my students, so if anybody else runs into these review sessions, enjoy. Although we have somebody's watching, but it says, somebody said, say hi. We won't say who, so I will say hello. So I've never actually, I should spell it right. Got a chat going on here, but that's okay. I'm just trying to center my screen here, so it's good to do while we're kind of bored here watching me try to angle my computer between the little AP Chem green notes there. That'll have to be good enough. A little crooked, but it's gonna have to be it. I don't even know which way I'm going here. There. So hopefully I won't right at the top where I'm too short anyway. So anyways, we're gonna go over in this one a lot of ideal gas law, PVNRT. I'll list all the gas laws and their names, but we usually aren't responsible for knowing Boyle's and Charles and all that. And then we'll use STP or standard temperature and pressure and how that's different than standard states, which is a thermochem kind of function. That's the little knot, the little circle, and how STP is not standard states, but it's similar. What else? And then we're going to go ideal versus non-ideal. So not really calculations with the van der Waals equation, but what is kinetic molecular theory and when do these gases deviate from ideal behavior? Okay, so that's it. So that's what we're going to do. So we're going to do problems again. I don't have the problems written down like last one. I actually wrote them down. So what I'll do is try to say the problem, and if you want to pause and try to work through it yourself, you can. So the first problem we're going to do, I'm just going to kind of read it to you, and I'll write some of it down. It says you have a reaction, and it has aluminum and oxygen. So what I'm going to do is give you less than what my students in the class right now can see. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 students here in the morning. They're suffering through sort of 3 hours. So am I. I feel like I'm suffering too. But it's worth it because we want to pass the exam. And you got to study anyway. So I was telling in the end of the last video, if you're studying and this is May 8th and it's like midnight, you waited probably too long. So we're doing this weeks ahead of time, trying to put in some time to maximize your score. And my hair is pretty crazy, so just ignore all that. I feel bad because I look over at like Troy here and he just looks like he just wants to go home, but he knows this is a good thing. So think of it like an athlete running 400 repeats. I did 400 repeats in high school. One time I think they made us do 10. That was insane. That wasn't enjoyable. But I'm pretty sure it made my 400 time go down by about a second or two. So it was worth it. So yeah, that was in high school though. I can't do that now. So that's fine. Here we go. So we're going to do 63. So we're going to take aluminum, put it with oxygen. So I'm going to have us do some balancing that, because we didn't do a lot of just reactions by themselves. So if you had to say what the products were, and this is going to be a redox reaction, so we could go completely rogue and go off to redox. We're not though. But what would the products be? So you need to know your charges. So I was telling to the other video, you need to know aluminum is going to be a 3+ and oxygen is going to turn into a 2-. And this is a synthesis reaction. You could say it's a combustion reaction too, but be careful. I've seen students tell me that this makes CO2 and water. So as chem teachers, we're like, that's the face, Abby. Like, where are you getting those elements from? But somebody made them memorize that combustions produce CO2 and water. Combustions of hydrocarbons, okay, not this, okay? So this is synthesis. So it's going to make, so hopefully you did this already. Aluminum would be 2 aluminums and 3 oxygens. There is no water present. So my students have a foldable that they basically say an ionic compound is either going to be a solid or aqueous at room temperature, but it can't be aqueous or aqueous if there's no water. So this makes a solid, okay? Then the next thing you need to do is you need to balance it. And we're not going to worry about the half reactions. You can do that separate. That might be a good way to take this to redox land. We're going to do this with a PVNRT kind of thing or gas laws. So we're going to focus on the gases. So it's 4 moles because you have to put a 3 here, which is a 2 here, and then a 4 here. So it's 4 moles of aluminum are going to react with 3 moles of oxygen and make 2 moles of aluminum oxide. Okay, a lot of times on the AP exam now, they give you the equation. I'm an old school person. I've been teaching AP, I think, for 17 years. So there used to be a question where they had to write the reaction, write the products, balance it, all that. That's gone. 2007, they kept it. I think 2014 is when they took those questions off the exam. So I'm kind of used to students having to predict it, so I still force them to do a little bit. Okay, moving on. So then what's the question all about? So this is where you should pause this after here. So 2 liters of pure oxygen. So 2 liters of pure oxygen. So number, unit, label, people, right? What is it? What's the unit and what is it of? So 2 liters of pure oxygen gas at STP. Now I'm going to show you how to do this problem 2 ways, which is something you wouldn't do on the exam, but I want you to pick which one you like. At STP, standard temperature and pressure, it reacts completely with a certain aluminum amount. So we don't know this aluminum amount. Now I want you to be very careful and tell yourself aluminum is a solid. Aluminum is not a gas. Do not PV-NRT solids and liquids. You can only use PV-NRT or all these little fun gas laws with gases. It sounds silly to say, but I've seen students try, and it's crazy. So then what we want to do is, it says, what's the mass of aluminum it reacted? So the easiest way to approach this problem is to use the fact that any gas at STP is 1 mole of any gas. Oops. Any, that's not how you spell any. Any gas is 22.4 liters of that gas. Now the reason this works is because the kinetic molecular theory states that gases are sort of, their size is negligible compared to the volume of the container. So if we're going to ignore their size, it's sort of like we ignore their identity. So I have named out who these students are today this morning, but it's almost like, imagine if I didn't care. They were just students. I just said whoever they are, I don't even care. So they could be, taller or shorter, but in the world of gases, it doesn't matter. They're negligible. So that's why this can be any gas, even the largest size gas particle and the smallest size gas particle. It doesn't matter, okay? But at STP, which means we are at 0 degrees Celsius. That looks really weird. So 0 degrees Celsius, which is 273. If there's anything you learned about gas laws, it has to be in Kelvin typically, okay? Unless you're going to use some kind of strange R value, but you just make it Kelvin, okay? Next is that we're at 1 ATM. Now, you can use different R values too. There's millimeters of mercury and kPa. On the AP exam one year, they wanted you to use, I think, the 62.4, I think it was millimeters of mercury. But what you can do right now is you can go PV-NRT or you can do Stoich. So I'm going to show you the Stoichiometry version first and then the PV-NRT second, because we did some Stoich last video, which would have been number 5. This is 6. So we'll stick with that first, and then we'll go back to using PV-NRT. So here's what you're going to do. You're going to say that I have 2.00 liters of oxygen. Okay? And I know that there's 22.4 liters of that oxygen if I have it at STP, which is 1 mole of oxygen. Okay? So I can switch out the any gas with the gas I'm looking at, which is oxygen. Then the next thing you can do is say that for every 3 moles of oxygen, I'm going to need 4 moles of aluminum. So if it's stoichiometry, you have to have a mole-to-mole ratio, or called the mole ratio. The next, you are going to then say, okay, well, now I'm going back to mass. And I think it's at 27 point, what is the mass for this one? 27 point, or just, yeah, it's 26.98. Unless it's a multiple choice, the numbers are really picky, I would just use 27. I think this might be a little hard for a no calculator question, but we could try. So 2 divided by that would put like 11.2 in the denominator. And then times, it'd be kind of tricky. So I think we're just going to say that, let's just say this might be on the FRQ or something. You have your calculator. So did you guys get an answer of 3.21? Okay. All right, so that's the one way we can handle it. I'm going to show you the other way right up here, which is similar but different. I always say PV-NRT is never going to let you down. And if you always just use it, you'll never get stuck using it when you're not supposed to, okay? So be careful with that. So this is the final answer. And then what I would do here would be saying, okay, if I want to use PV-NRT, be careful though. It has to be the pressure of oxygen, the volume of oxygen, the moles of oxygen, and the temperature of oxygen. You can't rotate between different particles. You got to stick with the same particle, in this case, oxygen. And it has to be a gas. I know it sounds so silly, but I'm going to say that so many times. It has to be a gas. You cannot use these facts right here or this if it's not a little g in the subscript there for a gas, okay? So we're going to solve for, we know pressure, we know temperature, and let's say we're not going to use this fact right here. We're going to take this one off the table, and we're just going to say, there's my volume. So treating it just like a gas law. Here's my temperature, and here's my pressure. So what are you solving for? We don't know our N, okay? And of course, we always have R because it's a constant. And so R, the typical constant, is that we use most of the time is 0.0821 liters, ATM, mole, and then Kelvin. So that's what we're going to use. So I'm going to isolate for N. So that's going to be P and then V over RT. I'm going to get rid of the labels for now. So the pressure is 1 ATM. The volume was 2.00 liters. And then the R is 0.0821 liters ATM mole Kelvin. I'm going to put that all in there. Kind of messy. And then the temperature was 273. So all I'm doing is putting in the STP conditions in there. Okay, so what we get when we do this, I'm going to have my students help me. So I don't actually know. I'm kind of just having this go rogue here, pulling out of the book. But what was the mole amount? Did you guys find that? Or somebody quick calculate on the spot?
8.92 times 10 to the -2.
Okay, 3.92 times, that right?
It should be
82?
8.92.
Oh, 8. Oh my goodness, Abby, it's my fault, not you. 8.92 times 10 to the -2? Okay, or you could say 0.0892 moles of oxygen. So then what you're going to do is then you do still have to do stoichiometry at this point. So I'm just going to erase this down here, okay? So this is where it's going to start to look like a little bit like what I erased. And then what you're going to do is you still need the mole ratio. I'm telling you that if you're doing a reaction and you're doing stoichiometry, you need a mole ratio. I'm going to even turn. You need a mole ratio, okay? So then 4 moles, so we still have that step. And then we still have the 1 mole of aluminum is 27 grams of aluminum. No, you can put a better mass there. But in the end, if you check this, I hope we get 3.21. Abby, how do we do? We got it again. Okay, so you get the same answer. The only thing is you head down the PV on RT path instead, okay? So this next problem, you're going to have to use PV on RT, so we're going to kind of apply that right away. We might be solving for something different. But anyways, you can find the result a similar way. Okay, so I'm going to read the question to you. Here it goes. So we have this 20-liter nickel container. So I don't know why they're telling us nickel, but it is. So it's a 20-liter container. It's charged with, I feel like it's going to go to court or something. But that means that they put it in there. Okay, so look for these weird words. 0.5 ATM xenon, 1.5 ATM fluorine gas at 400. The xenon and fluorine react to form xenon tetrafluoride. So I'm going to throw a little bit of Vesper theory back in here. What mass of xenon tetrafluoride can be produced, assuming 100% yield? So now here's a couple things, and we'll write the equation that makes this more difficult. We have 2 gases going in. We have a pressure of both gases, so it's a little bit of limiting excess going on here. That's harder than this one. Plus there's a reaction, and then we're not at standard conditions. I said they were at like 1.5 and 0.5. I'll write this all down. And then 400 degrees Celsius, so that is not 0, okay? All right, here we go. So what you want to do is write the equation down. I think it's another synthesis reaction, but it's not going to be a heavy combustion, though. So it said we're going to put some xenon gas and some fluorine gas. Probably the nickel has to do with the fact that maybe these won't react with it, because fluorine reacts with a lot of things. So I'm guessing if you're really a chemistry person, like why are they telling me nickel? That must be why. And then we're going to make it's diatomic. Don't forget that fluorine is one of the 7 diatomics. Okay. And then it makes xenon tetrafluoride. So this is an ionic compound. Or no, this is not an ionic compound. This is a covalent compound. So you just name it as it is or write it as it is. Now, again, on the AP test, they basically have gone away from this. I'm trying to find this question. you wouldn't know that this is a solid. That's just the way it is. So we can't PV-NRT that product, but we can use the gas law and the two reactants. So then here's what else we know. We know 0.5, sorry, xenon. And I'm not done yet. We got to balance the equation yet. And then we know 1.5. All right. And then what else do we know? That's it. Oh, 400 degrees. So those are our pressures. And then we're both of these are at 400 degrees Celsius. So immediately I would turn that into Kelvin. The other thing you need to do is you do need to balance it. So the balanced equation is just 1, 2, and then 1. Okay. So students in chemistry can struggle with gases and pressures. So if you want to keep it super simple, because this is limiting excess, we basically want to say, like, if I have a container, and these are going into the same size container, okay? So I'm going to put the volume here. I think I said 20 liters. So this is really the same container, but I'm going to show you something different. The pressure would be, you'd have some cute little gauge of, like a little gauge up here would read the pressure. Don't grade my art here, people. Okay, so like a little arrow or whatever. And then the thing is, let me just make the arrow here a little higher. That. Or if it has a digital gauge. The one has way more pressure than the other, okay? So that means inside of here, if the volume's the same, there have to be a lot more particles in that one compared to this one, okay? Now, really, if you're doing kinetic molecular theory, they're moving around randomly, constantly. Their average movement is the temperature. The average kinetic energy is the temperature. They have elastic collisions. They have no intermolecular forces. So that's how the intermolecular forces comes back. We're going to say they don't. They don't have any attractions or repulsions. Collisions are elastic. All that stuff, which is sort of slightly lies. Okay, so we got to keep going. So what we need to do is figure out which one of these gases is the limiting. Okay. Now it's a 1-to-2 ratio, so I'm just going to kind of go for it because we just did limiting excess. The number of pressure, or the pressure unit, relates to the moles. Okay, so the moles here is less than the moles here. So what I'm going to do is just say, how much bigger is 1.5 compared to 0.5? 3, right? So what I'm going to quickly just say is the ratio is 1-to-2. And the pressures are 1-to-3. So who do we have more of probably than we need? We have more fluorine gas than we need, okay? So if it was the right ratio, it would be 0.5 and 1. And that would make it be all completely consumed, okay? But either way around it, you could have then still used the 0.5. So the whole point here is we need that pressure, okay? So this is our pressure of xenon. This is our temperature. Oops, what am I doing? Because the door is open, I'm getting worried about somebody wants to shut that. I'm getting worried about the volume out there. Freshmen we're done torturing them. They've done their time. So they were taking tests, we were learning chemistry. But we aren't going to use the 1.5 because it's excess. And we could do the math to prove this, but let's just kind of eyeball it and go for it. That's usually what this will be on a multiple choice anyway. So here is what we're going to do. We've got, we want to find then the exact moles. And then when we find the exact moles, we can turn that into, because I think the whole point of this question, if you didn't write it down yet, yeah, what mass of this can be produced? And it is mass, so that means it's a solid. This might be the only question we do. All right, so let's keep going. So we're going to do PV equals nRT. And then again, we're going to focus on xenon. It's our limiting. We want to find N, just like last time. So it's PV over RT. So this looks like the last problem that we did. We're going to put in 0.5, but we're not at STP. Volume is 20 liters. So hopefully my students are getting a calculator. And then we have 0.0821 liters ATM mole Kelvin. And then temperature, be careful, we got to add 273. So is it 673? All right, you guys help me here because I'm really, my voice is going here. Okay, so what mole amount do we get here? And I didn't want to go rogue. Sometimes I make up questions. I said that in the other video, but I don't want to do that with this because these are too challenging to do that. 0.181 is that what you guys get? That's what this source says we should get. So that's our xenon's mole amount, but we're not done. And then this source just talks about if you were to use the xenon, or sorry, the fluorine, you would get a mole amount that's too high. And you basically would prove that the xenon is limiting. So if you took a lot of time, you could redo this whole calculation and get a moles of the other one, and then you could do the mole ratio. But if you've got a gut feel that this is limiting, then I would just go sailing, because you got to just not worry about always checking everything, okay? So what they're saying is you could redo this all and do this, you know, then you get a mole amount, and then you could compare and prove that really this is the limiting. That's a lot of time. Okay, let's keep going. We're almost done though. 181 moles of xenon. And I just have a really quick question I'll talk about at the end. And then we're going to say that we have for every 1 mole of xenon, this is nice, we have 1 mole of xenon. Oops, and I would put it, even though it's 1-to-1, if it was on the multiple choice, nah. But if it was on the FRQ, absolutely, okay? So then we're going to say that for every 1 mole of xenon, whew, geez Louise, I'm having a hard time here. What's the mass of that? Let me find it. The molar mass of xenon. It's not really something we usually ever take the molar mass of, huh? 207? 0.28. Yeah, I'm just going to fit that. And then what you guys get as a final answer. Check if we got it right here.
37.
Yeah, 37.5. And 6 big wise, there's our day. But we're good. They're going to lunch now. We'll have lunch in just a second here. So 37.5 grams is the mass of that xenon tetrafluoride you can make. So just because I want to wrap all of these videos back around together, there's 6 of these things. I want us just to quick draw a Vesper for this. Because it's an expanded octet, it's one of those we haven't dealt with yet. And I would say that the AP test could take you here, okay? So what I'm going to do is go way back to how many dots would this have? So 7 times 4 is 28, right? What's the total number of electron dots we would place? Was it 36? And then really we're going to deal with 18 pairs, okay? So xenon's going to go in the middle. The one thing that you should be kind of weirded out about this is that you're making xenon bond. Okay, now the first thing that you're going to do is you're going to go there. And that's okay. This is a dot structure at this point. It's not 3D. You're used to going top, bottom, left, right. So then you're going to go 1, 2, 3, 4. I've taught my students that typically halogens are going to have 3 pairs of lone pairs. So do that and dole out all of those. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But how many do we have? So 36 electrons or 18 pairs. So what do we have left? 2 pairs. So what's the rule? This has happened a lot on the AP exam, and students will go, I'm not putting them. Okay, well, you're wrong. And they clearly have said the pairs. They know, but then they're like, I can see their faces just that day going, I don't know where to put them. They go on the center atom, okay? So then you kind of just say, okay, they go here and here. Maybe you make room at the table. That's what you do. Make room at the table. Josh, this is an expanded octet. He's writing this down, okay? He's never seen this before. What in the world does this turn into? So if you want to go back to the video where I said it is important to know what's called the electron geometry and the molecular geometry, okay? The electron geometry is, ooh, that's bad. The electron geometry is octahedral, okay? This is going to be coming out at you. These are going back into the board. And these are sort of in the plane, okay? Here's your center atom. That's your xenon. Here are your outside atoms. Those are your fluorines, okay? Could this deviate from ideal behavior? Man, add up all the electrons? Possibly, okay? So even if this thing is nonpolar, which it's going to be in a second, Josh, it still has a lot of electrons. It would have LDF forces. If it's a nonpolar molecule, it would only have that. But it could have that whole polarizability. And the whole point of PVNRT is that the big thing that the AP test wants you to know is that some things deviate from ideal behavior. If they have a high intermolecular force, they're going to deviate. If they're large molecules, they're going to deviate. If they're really cold, they're going to deviate because they're getting so tight together and they're slowing down. If the pressure gets really high, they're going to deviate, okay? So make sure you're aware of when they don't follow the rules, okay? Then what you got to do, Josh, is you want the electrons to go in the largest bond angle. Now, for this one, it doesn't matter, but hear me now. The electrons go in the biggest bond angle. So right now, they're all 90s, so it doesn't really matter. Most people say these lone pair electrons, we're going to put them here and say that that's not a bonded atom. And then what is the name of this thing? So the angles are 90s. Okay, these are all 90s. Oh, we don't know. So square planar. And it would be nonpolar because you've got these electrons being pulled out and out and out and out. They would be in what's called a vector summation. They would cancel. So this would be a nonpolar molecule, LDF. But what's the state of matter? That proves it. Like, this is a good question if you add everything in. And that's what's going to happen on the AP test. It's not just going to be just gas laws. A to B, I, triple I. Man, one time I think they went to J. It's like, who wrote this? So maybe not to J, but I don't know. There was a lot. Okay, so they're gonna take maybe xenon and they're gonna go rogue. So you might be PVNRT. You might go over here. If this is a synthesis reaction, it can be redox. Oh my gosh, they could take you anywhere. Okay, keep going. So this is going to be nonpolar. And what's the state of matter? Solid. So this has to have those polarizable induced dipoles that are impressive. And so they might ask about something like that. What makes this unique? Okay, this was a much shorter session, which is fine. The one thing I do want you to know is the deviations from ideal behavior. There's a van der Waals equation you don't have to use, but you do need to know why you would use it. And the last thing I didn't cover, and I think I might just throw it in just in case some of these students do want to stay. We had one leave, but that's okay. This last one's really easy. But man, when you first see it, you're going to be like, I don't want to answer this. I don't know what to do. Okay, so let me quickly do one more. And I'll just try to just tell you right to the point, okay? The good news is nothing's reacting in this question. They're just mixing two things together, okay? So we are going to look at this. So they're going to say we have a partial pressure of methane. Okay, so you're going to have methane in a container, which is tetrahedral. We went through that already, which is 0.175 atm. So that's its partial pressure. You have oxygen. This one's really fast, which is linear double bond, nonpolar, atm, 0.250 atm. So you know what's called the partial pressure of each. Okay, this is going to be Dalton's law. Dalton's law, a lot of students see it and they're like, oh, it's so simple. And then they don't know how to do it. Okay, so don't get cocky with Dalton's law. It says, what's the mole fraction of each of the gases? Okay, so mole fraction is this. So if I had a mole fraction of oxygen, it would be the moles of oxygen over the moles of oxygen plus the moles of methane. Okay, and if I had the moles of methane, it would be the same thing. However, the easier thing to do is say the moles of methane is 1 minus the mole fraction of oxygen. If you wanted to put moles of methane on the top, you could go ahead, but it's easier just to say there's only two things in this container. So if I know this one, then I subtract this from 1, okay? But all you have is pressures, okay? So this is the equation on the AP test that's sitting there. And I actually thought it looked a little bit like something called Raoult's law, but it's not. It's a version of Dalton's. So if I know the mole fraction of A, I can take it times the total pressure, and I can get the pressure of A. Here's the deal, though. We have the pressures of sort of A and B, and we can add them and get a total. So what's our total pressure? So if I put these two things in a container, they are not reacting. So I have tetrahedral methane in a container. I have linear oxygen in a container. I have probably more oxygen than methane based off of pressure, okay? They're bouncing around. They are not doing what? Chemically reacting, okay? So they are not chemically reacting, just smacking around, okay? So we're not making it combust, although could it? Yes, okay, we could. We're not doing that. So what would you do? Here's the thing. You take pressure of A divided by pressure total, and you get the mole fraction of A. They're having you rework this equation. This is the kind of sneaky stuff they're going to make up. I'm telling you right now. So what would you do? So P, let's say it's oxygen. So we're trying to find the mole fraction of oxygen. So let's switch this out. So we just need to put the pressure of oxygen over the pressure total. Well, how do I find the pressure total? Just add them up. So what's the pressure total?
425.
425. So pressure of total, okay? So the math is going to look like this. I'm just going to go this way with it. So 0.250 ATM divided by 0.425 ATM. So what's your mole fraction of O? Don't be scared of this question. Again, there's just a little more O than the methane. So this just puts it in a fraction. I love mole fractions. What is it? 0.588. What does the book have? I kind of have the answer sitting here too somewhere. Where did it go? What are we doing? Which one are we doing? Try to make it fast here because we all want to go home. We're done with this.
Yeah.
Oh, yeah, 588. Okay, so we have that one. And then what's this one going to be? So I don't have numbers to do this. This is 3 different numbers. And right now I don't have any, but I can still solve for the ratio. Then what's this one? Just 1 minus, which is 0.412, and we're done. So we really will never know the actual mole amount. We might be able to try to push it and try to figure it out, but we don't even care, okay? And that's pretty typical. It's a good multiple choice question, but they'd have to make the numbers easier. And they could. You know, they just aren't going to do like this. They might do 0.2, 0.3, or something that adds up simple. And then dividing these, you just have to be careful. So don't forget about this kind of stuff. Like, you know, how would I divide like 1/2 from 1, well, we got to be bigger than that. So 1/2 from 3/4 or something. So go back to simple tricks with fractions. How would you get an answer for that if it was 0.5 and then 0.75? And you could. You know what to do, right? Okay, if you don't figure it out. Okay, that is enough for today. That's 30 minutes. I'm glad you guys came. I'm glad if anybody watched it, you watched it. Bye. Will I make a session 7, 8, 9? I don't know. Maybe. What would it be? We'd go on then to thermochem, kinetics, equilibrium, all the really AP stuff that we would learn in our second year class. Goodbye. See you later. Thanks for watching. If you watched, good luck. Okay.